Welcome to our biosphere. It is heavily impacted by the atmosphere, surface, and the sun. To understand CO2, we need to see CO2. To do that, we need to become quite small. Let's shrink ourselves 100 million times. You okay? We are looking at a cube of space measuring 40 angstroms across. A stack of 1,000 would be nearly as tall as dust. But we still can't see CO2. That's because molecules at normal air temperature are zipping around faster than the speed of sound. And since we'll be dealing with photons, let's slow down time by 200 quintillion times. Ready? Now we can see. Meet your new friends, nitrogen and oxygen. A word of caution about your new friends. Oh my gosh, don't let them drive. Each one crashes into another 5 billion times each second. Each time they crash, they exchange energy, or in a case of greenhouse gases, give up a photon. And no worries, your friend CO2 left to go shopping for photons. We'll find her later. This is what happens to solar radiation when greenhouse gases aren't around. Nitrogen and oxygen were relatively unaffected by the long-wave emission. Let's go find some CO2. I looked at 40 cubes, nothing. Where is she? But I did find this, H2O, moisture. Let's fire a photon. This time, the long-wave emission was captured by moisture. We've felt this before when the air becomes muggy and then gets hot. H2O is a broadband greenhouse gas. It absorbs more than 4 times the bandwidth of UV emissions from the ground. It is also about 10 times more abundant than CO2, making it more than 40 times more effective at insulating the atmosphere. But let's keep looking for CO2. It took a while, 700 cubes later, but there she is. Let's fire a photon. What happened? CO2 is a narrowband greenhouse gas. It absorbs only a few emission frequencies. That photon was at the wrong frequency. But don't worry, H2O will capture it. Let's fire another photon. Ah, another wrong frequency. Let's fast forward to an emitted photon with the right frequency. This time, the long-wave emission was captured by CO2. The photon frequency was within the narrow band that CO2 can capture. Let's explain this using an accurate parallel. Insulation from your attic helps insulate from heat loss, just as CO2 insulates the atmosphere from heat loss. Let's bring the insulation down so we can see its cross-section. The pink insulation represents the insulation from atmospheric moisture. The black line represents the added effective insulation from CO2. Now let's double CO2. Doubling CO2 only increased your insulation by 3%. Compared to H2O, CO2 is 1/4 as effective and 1/10 as common, giving CO2 only 2% of the power of atmospheric moisture. So it is no surprise that the empirical evidence shows that H2O's greenhouse property plays in the major leagues, while CO2's greenhouse property plays in the minor league. On the bright side, CO2 plugs a hole in the frequencies that H2O captures. Let's explain that visually. On the horizontal axis is photon wavelength. Up is higher photon energy. Here on the left are the high energy UV photons that give you a sunburn. These are the photons or sunlight wavelengths that you can see from violet to red. On the right, we get into the infrared low energy photons. Also on the vertical scale is a quantity of photons. The quantity of photons for each wavelength of light coming from the sun follows the shape of the black line. Notice that the peak in quantity are those photons we can see and that express themselves in various colors. But not all of those photons make it through the clouds to reach the oceans, flora, land, and us. It is mostly moisture that catches many photons and creates the deep valley shown in the yellow line. The quantity of photons that Earth's surface emits back toward space follows the red line. Notice how these emitted photons are low in energy. H2O, atmospheric moisture, catches high energy photons here, 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 and all along here. Remember that you were told that CO2 plays an important role in plugging a hole for H2O? Well, that hole occurs here. But notice that this is where there aren't that many photons, none from the sun, and that these photons are all low energy. H2O catches high energy solar photons and low energy surface emitted photons. H2O is like an entire outfield catching all of the balls and line drives. That is why H2O is so powerful. We've studied the interactions of photons with the greenhouse property of CO2. Now let's look at its alter ego, the green property of CO2. The green property of CO2 includes the interaction of CO2 with flora. CO2 makes flora healthy. CO2 makes flora grow. While current CO2 levels are okay for C4 type flora, C3 type flora are suffocating. The parallel for C3 flora living on 420 ppm of CO2 is like expecting humans to live on oxygen levels found at the top of Mount Everest. C3 type flora grow about 58% more with each doubling of CO2, and the majority of all flora is type C3. C3 flora includes all trees, most grains, and most cool season grasses. So changes in atmospheric CO2 has a huge impact on the growth of flora. An attribute of flora where some miss the point is albedo and reflectivity. They don't see the full story. This is the reflectivity of an ice sheet. Notice how well it reflects incoming solar energy back to space. This is the reflectivity of vegetation. Some point out that in the high energy area, vegetation doesn't do as well as ice sheets. But that void area isn't void. That is where flora does its thing with incoming photons. It converts photons into sugars in a chemical process that allows all forms of flora and fauna, including us, to grow. When we add in those photons that get used up, we get this curve for total albedo plus. Suddenly, flora looks better than ice sheets. Well, you ask, what about flora in northern regions where flora goes dormant? In those regions, flora cover is replaced with snow cover that reflects like this. Flora, everything about it screams, protect me. I need to breathe. Please. Sorry, I need to pause. Too often, I see the staggering capacity for human air and the unintended cruelty that brings. But you can be the cause of hope. Greenhouse gas molecules are like bumpers on a pinball machine that sends photons on a long route to outer space. That traffic delay is why greenhouse gases are insulators, just like the insulation in our attics that delay the loss of heat. Let's fire a photon from the sun to see the greenhouse gas process. Watch how one high-energy solar photon spawns 8 terrestrial low-energy photons. How does that compare to flora? First, flora eliminates solar photons by reflecting some back to space before they turn into radiation that interacts with greenhouse gases. Most is used to grow flora. The sun produces high-energy photons. If allowed to hit ground, each of those photons can create about 8 low-energy photons at a frequency that CO2 can temporarily capture. So for every photon that flora uses or reflects, CO2 sees 8 fewer photons. 8 to 1 is leverage of CO2's green property. A small change in flora has a huge impact on the greenhouse gas effect. Flora is powerful because it reflects and steals high-energy solar photons before they have a chance to interact with greenhouse gases. Missing from energy balance diagrams are climate effects from flora. Maybe this will get the ball rolling. In 2010, there was downward shortwave radiation, some of which was reflected and some used up by flora to power its growth. The remaining was radiated upward as long-wave radiation. That same process is then repeated in 2020 with about 2% more leaf area per NASA data. The result of a large jump in CO2 in the past decade is that the green effect of CO2 caused about a 1 watt reduction in long-wave radiation, which overpowered the 0.4 watt increase from CO2's greenhouse effect. You know this is true because you found the comfort of shade on a hot day. You know this is true because you've taken cool walks through the woods. You know this is true because you've madly run on tiptoes across the hot sandy beach. You know the grass is cooler. And that is just the flora part of the climate cooling property of CO2. There are also aerosols associated with industrial CO2 that cool by reflecting solar radiation back to space and by aiding in cloud formation. Let's summarize all scientific research on climate change and CO2. Many studies, like this study, confirm that CO2 has a greenhouse gas property that forces climate. No debate there. But what about CO2 in total when all climate change properties are taken into account? There were 4 studies on the total effect of CO2. All conclusions were the same. CO2 in total did not cause global warming. This study, the only one to include hourly and monthly climate data, short and long-term horizons, and every international climate data set, agreed with those studies. CO2 did not cause global warming in the past 6+ decades. This study also found that while CO2 in total doesn't force climate, methane and atmospheric moisture do. This study also put together the clues and physics as to why the greenhouse property of CO2 overpowers its greenhouse property, causing CO2 in total to anti-force climate. To explain this to friends, tell them the truth. Scientists have always known that CO2 has multiple climate effects, one that warms and two that cool. It was recently, in the fifth study on total CO2 effects, that scientists confirmed that the cooling or green property of CO2 is stronger than its warming or greenhouse property. The rise in CO2 has cooled the planet more than it has warmed the planet. The limit of this study is that it only showed total climate effects for greenhouse gases. Later studies will be able to break down the effects further to finalize the physics.